And good evening, AP Physics students. Mr. Gerson coming at you here. Going to look at Chapter 17, problem number 2 today. Alright, so we're going to introduce a new idea today in electrostatics called electric potential. You may have heard this referred to as voltage. Voltage isn't a really good term to use in physics. We prefer electric potential, but that's the units of it. So electric potential is electric potential energy per unit charge. So its units, the units of potential are a joule per coulomb, which kind of makes sense since U is potential energy measured in joules and Q is charge measured in coulombs. But we get tired of saying joule per coulomb. So 1 joule per coulomb is defined to be 1 volt. So voltage kind of makes sense as a unit. We just don't use it a lot. It's kind of like saying newtonage for force. So you will hear electric potential referred to as just potential, or electric potential, or voltage. Now, don't get confused between electric potential, which is measured in volts, and electric potential energy, which is measured in joules. Two different units there. One more piece of background information here before we get to problem solving. Back in the day when we were looking at gravity, we defined the change in potential energy on a conservative force, an object that a conservative force is doing work on, as negative the work done by the conservative force. For example, when we calculated what the gravitational potential energy of something is, we calculated the work done against gravity in moving it to that new location. And work was force times distance. So the force of gravity was mg, or the weight, times the distance moved against gravity, which was y. So we are going to make use of this little guy during the problem here, because the problem is going to ask us to calculate the work done on a charge by moving it from an area with a potential of 125 volts to negative 55 volts. Now, just to give you an idea of some different voltages around there, here's a here's a AA battery, and you can see on there it's got a voltage of 1.5 volts. It says that on there somewhere. Where does it say that? I forgot where it says that. Well, anyway. Right there. It's really hard to see. 1.5 volts. Right? A car battery is 12 volts. Outlets in most U.S. households are 110 volts. So just to give you an idea of some different voltages there, I kind of think of voltage as like electrical pressure or electrical push. Right? The more voltage, the more charges are being pushed through a region. The power lines, transmission lines might be 10,000 volts. Lots of electrical push. Right? 1.5 volts, I can put my fingers on the end of 1.5 volts and I don't feel a thing. Okay, let's enough background information. Let's get to solving this problem. Problem number 2. So, it wants to know, I have a region where I have 125 volts, a region I have negative 55 volts. I have a positive charge, and this positive charge moves from 125 volts down to 155 volts. If I wanted to, I could draw in the electric field here. Notice that the positive charge would be moving with the electric field, because that's what they do. Okay, so if voltage is electric potential energy per unit charge, we could also write that as negative the work done per unit charge, since these two things are equal. So rearranging this equation here, I could get work is equal to Q times V, or sometimes we write this as Q times delta V. because to do work, I have to change the voltage or move the charge through a potential difference. Okay, so how much charge do we have? Well, in this problem, it says that we have a proton. Oh, and I forgot my negative sign in here, right? From negative sign being there. The work done, it would be the charge on a proton, 1.6 times 10 to the minus 19th coulombs, times the change in voltage. Change in voltage means the final voltage minus the initial voltage. Now, let's double check our units here. Charge is in coulombs, voltage is joules per coulomb. So we should get this to come out to be joules, which is what work is measured in. So that's good. So what is this? 1.6 times 10 to the minus 19th times, this would be negative 180. We got a negative there and a negative there, so that makes a positive. So the work done turns out to be 2.88 times 10 to the minus 17th joules is the answer to part A. Now, I always like to double check my sign here. Is the work positive? Is the work done here positive or negative? Well, what direction is the electric field pushing the positive charge here? Well, it's pushing it down this way. So the direction it's moving is in the same direction that the force is being exerted. When that happens, right, force and displacement in the same direction, that's positive work, right? So yes, indeed, we should have a positive sign here. So just as something I always like to keep in mind, positive charges tend to go away from positive voltage towards negative voltage. Another way to think of it, if you have a battery, here's my battery, right? Usually the negative terminal we think of as being 0 volts, and then the positive terminal as being the voltage of the battery, or 1.5 volts. So, you know, what direction would a charge go in this situation? Well, a positive charge would move away from this terminal, right? Be repelled by the positive terminal and be attracted to the negative terminal, right? So positive charges tend to move towards smaller potentials or decreasing potentials. A negative charge, remember, would move towards an increasing potential, right? It would experience a force that way, a negative charge would. Okay, I've got one more thing to talk about. The problem says calculate the work both in joules and electron volts. 1 electron volt, or 1 EV, is a unit of work or energy, and it is defined to be 1.6 times 10 to the minus 19th joules. Now, why would we define such a thing when we have such a good unit for energy, joules, anyway? Well, it's really convenient to use this unit. Where does it come from? Conceptually, it's the amount of work done to move 1 electron through a potential difference of 1 volt. So it's just what it sounds like. 1 electron volt is the amount of work done, or work needed, to move 1 electron, right? 1 electron through a change in voltage of 1 volt. So it's just what it sounds like. And so, for instance, I could do this problem here without my calculator. Here I had a charge equal to the charge on 1 electron, right? 1 proton, same charge, different sign. How much work would it take to move it from 125 volts to negative 55 volts? Well, the work would be 180 electron volts, right? Because my charge is the charge on 1 electron, and the voltage is 180 volts, so the work is 180 electron volts. And if you want to double check, you could always use this as a conversion factor to convert this guy to this guy. All right, nice work, AB Physics students. Here's your joke for today. So, Mr. Kirsten, how was your break? Well, during break, I changed the light bulb, Then I crossed a road, and then I walked into a bar, and I realized that my whole break was just a joke. Get it? Because those things are typically starts to jokes. All right, good work, physics students. We will see you tomorrow.